One car is heading down the road towards a collision, unaware of the dangers ahead, for another car is approaching the same intersection, oblivious to its presence. It's a scenario we have seen played out too many times on our roads. The two cars crash, and the consequences are dire. What if there was a solution to prevent such tragedies? The Radar Sensing and Joint Communication Project represents a step towards this solution and would be crucial for the advancement of autonomous driving technology. In this project, the car radar systems are adjusted in such a way to allow communication between them. This way, the two radars can exchange useful information about their respective cars, such as GPS position, direction, and velocity, which would alarm the drivers about a possible collision and allow them to implement the necessary countermeasures. The two radar antennas seen here would represent the RF front of the communication system, while the FPGAs would take care of generating the information payload and decoding information coming from the other car. To do that, we acted on the VHDL code representing the project and modified the logic accordingly. The FPGA is then reprogrammed by the PC running the application and is then able to perform the required tasks. Finally, the system is tested in the lab by using an oscilloscope that shows the transmitted and received signals by the two radars facing each other to check that the payload is present and correctly received. Our project is a step towards a safer and more efficient future for automotive radar systems. By combining sensing and communication, we can enhance cooperation of vehicles, improving the safety and comfort of drivers and passengers.
Welcome to Automated High-Speed Optical Link Testbed for Datacom Transceivers Project Presentation. The aim is to provide reliability and efficiency to optical measurements through automation. This means, based on a real laboratory setup, controlling it remotely through a graphical user interface, performing measurements and showing the results. Different experiments can be carried out thanks to a hold simple GUI. Let's start from the bit error rate curve measurement. For each received power, set by the user, the corresponding bit error rate is measured and displayed. You can follow in real time the measurement process with the help of progress bars. The displayed points are taken weighting to detect a minimum number of errors set by the user. The weighting procedure cannot exceed the maximum time value. When the process ends, the plot can be saved, and the measurement can be repeated editing the parameters. Other than BER measurements, it is also possible to analyze optical devices' behavior. For instance, here the optical filter characterization is carried on. Changing the laser wavelength, the received optical power is measured and plotted in real time. User can set the wavelength interval of interest in the step. In this way, hundreds of points can be measured easily, obtaining a very high granularity. Indeed, automation allows to reach the double goal of obtaining high precision and accuracy, while saving time to carry parallel activities. After ending the filter characterization, some useful parameters such as bandwidth and central frequency are provided. Thank you for your attention and good luck to future students.
In recent years, the frequency and severity of geotechnical events, such as avalanches and debris flows, have underscored the urgent need for innovative early warning systems. This project approaches the problem relying on optical fiber sensing, offering a cost-effective solution.
A light beam is generated by an optical laser and it is splitted among two fiber cables through an optical splitter. An optical switch, driven by a national instrument board, is also introduced to periodically change the optical path. A polarimeter acquires the polarization information and sends them to the user via USB cable for MATLAB processing.
To reproduce a mountain environment, a reduced scale-downing model is incorporated in the system to test scaled events. The model is 55 cm high, 1 meter large and 30 cm wide. Dangerous events have been simulated by rolling stones on the model.
A graphical user interface has been designed to enable easy control of the system parameters through the possibility of choosing them within a suggested set and real-time plotting of angular speed variations. A red traffic light and an audible alarm alerts the user promptly.
This project proved that the optical fiber is a good sensor for mechanical vibration detection. A reactive single fiber system has been designed at low cost and with high performance and reliability. Also, a two-fiber system has been implemented and tested, showing a good capability of discriminating different fibers' contributions, but not a suitable reactivity. Further improvements will be so oriented towards the design of a multi-fiber system able to work in real time.
Welcome to our presentation on Open Optical Switch, where we delve into one of the switching mechanisms within optical communication with the aim of enhancing network control. Our project utilizes reconfigurable add-drop multiplexer, equipped with two wavelength selective switches, all controlled using Python. Our project revolves around three primary objectives. Firstly, we implemented routing and wavelength assignment to foster flexible and efficient resource utilization. Secondly, we optimized network performance through spectrum flattening. Last but not least, we investigated the filtering penalty introduced by WSS by analyzing the optical signal-to-noise ratio and plotting it versus bit error rate. Routing and wavelength assignment involved transmitting a simulated signal comprising only IZ noise across 96 channels, spanning from 191.3 THz to 196.1 THz. This signal traversed from the demultiplexer of the first WSS to the multiplexer of the second one through a designated port. Additionally, we conducted an experiment to drop a specific channel centered around 194 THz to further explore the capabilities of the ROADM. For spectrum flattening, we utilized an optical channel monitor to capture power levels across each channel, subsequently adjusting the attenuation of individual channels using a variable optical attenuator. This process resulted in a maximum difference of 0.6 dB between channels, confirming the achievement of a uniform power distribution across the spectrum. In our third experiment, we analyzed the filtering penalty of the wavelength selective switches by evaluating the OSINAR versus BER plot. OSINAR computation involved measuring IZ noise power within a designated bandwidth, accounting for channel granularity, and subtracting the noise power from the power of the modulated channel within its bandwidth. Our findings revealed that to maintain a target BER of 10 to the power of -6, an approximate 3 dB increase in OSNR is necessary to compensate for filtering effects. Furthermore, the filtering penalty was found to be even less when considering the granularity of the